So we're going to pick up where we left off with projection at an angle. I know we've done a little bit since then, but what we've done is an experiment on projection at an angle. Specifically, as we've discussed, case 1. We've looked at this scenario now. Now, last lesson, if you were moving a little bit slow and you didn't get that lab document finished and all of those discussion points answered, I do want you to put in the effort today to make sure you don't fall behind on today's lesson and have stuff to catch up on today, because if you keep doing that every lesson, you're just going to have a pile of paperwork to catch up on. Yeah, you've already got your chapter reviews, you should be working through that. That should be what you're doing for homework, not catching up on a lab report that we could have finished in class, and certainly not catching up on exercises that we should be able to get through today, okay? So we've looked at case 1 and we went through that methodically, step by step, looking at how we can, in this example here where a bullet is fired from a rifle, and this is a situation where it's case 1, even though we haven't necessarily made that explicit, we do have the situation where we're landing at the same height as our launch height. And we found these few things. So initially, just splitting up our vector component of initial velocity, u, into its horizontal and vertical components, okay? Very important skill, being able to break those vectors down to their component forms. Looking at the maximum height, and because we know a lot of information about that maximum height, that's very easy to do. One thing to remember is to keep your vertical and your horizontal components totally separate. They behave totally independent of one another, okay? So remembering that, we can easily just imagine the situation where we're throwing a ball directly upwards and it's falling straight back down. It doesn't matter that it's also traveling horizontally. That's a separate thing, okay? Often the thing that ties our horizontal and vertical components together is purely the time, okay? If we know the time of flight, we know how long it takes to go up into the air and land again, and we know how long it takes to travel horizontally. That ties everything in together. We can easily find out, and we did this as the last thing, the horizontal displacement there, S of x, that was our last thing that we had to find, and that was so easy once we knew how long we were in the air for. Because if you know how long something's flying for, and you know how fast it's going horizontally, which doesn't change because we're never going to deal with accelerating horizontally. We don't deal with air resistance. In physics, we'll be focusing on negligible air resistance. That becomes such a simple calculation. Just how fast are we going, how long are we traveling for? All right, that's how far we went, okay? Now, we are going to jump into this second example here today. So can everyone please go to that and make sure their notes are set up for that one? We're going to talk about the case where we actually land at a distance lower than our launch height. Now, the first thing we're asked to find is the time of flight. The second thing is the impact velocity. And the third thing is the horizontal displacement. So immediately here, we're jumping into the time of flight because obviously, for obvious reasons, that's going to be very useful. Okay. We're going to have less scaffolding here. So we're looking for t. Find t. That's our goal. And specifically, we're looking for a t that refers to when we do this. And we land with some negative vertical displacement, sy. Okay? And that's going to be a key thing. Our ball has started at a height and ended up going negatively in displacement. That displacement has a direction, and it's going to be downwards, which we're going to set as negative. So all of our vector components here, we have to establish that we have positive upwards, and we'll just stick with a convention of positive to the right as well. And again, those are arbitrary. You can set them to be how you like. There'll be problems we look at where cars collide into each other. We've done this before, right? We could say that's the positive velocity and that's the negative velocity. It doesn't matter. As long as we set that before our problem before we begin the problem. Okay, find t. Now, I want, as a bit of an exercise, you guys to just look at this, and you can think back to how we found t in the last one, and think about what's different in case 2 that means we might not be able to do things exactly the same. So this is where we started finding t. We knew all of this, so we used this formula. Now, you look at that formula and you think, in case 2, do we know all of this, okay? Do we know our initial vertical velocity? Do we know our final vertical velocity? Let's have a look. So we're considering using the same formula, which is Vy equals, and you should have your formula and data book in front of you. I forgot to bring mine, so let me just bring it up digitally. Should be looking at this one here. Oops, gone, nope, there it is. Vy equals gt plus uy. This is the one we used before. So Vy equals gt plus uy. Okay, that's what we used previously. Is that usable in this case? No, why not? What's missing? What are our knowns? We obviously want to find t, so that's obviously missing. Hopefully that's the only thing missing. G we obviously know, that's just the acceleration due to gravity, negative 9.8. Negative 9.8. Initial vertical velocity, do we know that? We don't, but we can pretty easily find it, yeah? We have our initial velocity as a vector. We can easily break that into Vy and Vx, oh sorry, Uy and Ux, right? That's not an issue there. We can easily do that. So yeah, maybe this formula is usable. What about our Vy? No, we don't know our Vy, okay? Because what we did in this previous problem is we set our Vy to be either 0, right? Vy at this point equals 0, or our Vy over here is just equal to the negative of our Uy. You'll remember that as an important property of case 1. However fast we're going upwards at the start of that is exactly how fast we'll be going downwards by the end of it, because the amount of time we spend accelerating should be perfectly symmetrical. Okay? That's not the case here. We spend a lot longer accelerating downwards. So our final velocity downwards will be a greater number in magnitude than our initial velocity upwards. So what else could we use? Let's go back to our formula and data book. What's another thing we could consider? This one here, what do we think? Is that worth assessing? Yes, possibly. What about this one? Would this one be worth assessing? No? Why not? It doesn't what? We don't know Vy, right? But we know G, we know Sy, we know Uy. Can't we solve for Vy? There's no t in there, right? So not particularly useful because there's no t in there. However, it does give us Vy, which we just established from this formula. We want Vy. Gives us Vy squared, so we take the square root of both sides, we get Vy. Now, here's the thing. We could do this problem right now with this. What do we end up solving when we have t squared and a t like that? Okay, a quadratic. We end up having to solve a quadratic equation. Things can get kind of messy. You can do it. There's little cheaty ways you can do it where you divide by t, but you can't technically divide by t because you don't know if t is 0 and you can't divide by 0, so it's technically not allowed mathematically and it's bad practice. With this problem, our immediate solution is to solve for Vy using this formula, okay? So let's actually do that now. We're not going to be using this yet. We don't know Vy. So let's solve for Vy so that we can find what our question is, which is t, okay? We're first going to need Uy because this formula will use Uy as well, so let's do that. So Vy squared is the formula we're going to use, which equals 2gsy. 2gsy plus Uy squared. So let's quickly solve for Uy squared. So Uy, or sorry, just for Uy. Uy is going to equal, it's our vertical component here. So if we imagine it over this side, yeah, there's our angle. It's opposite the angle. So we're going to be using our sine, our rearranged sine formula. So U sine theta will give us our Uy over here, our opposite, okay? If you'd like to, off on the side of your page, I'm not going to do it, but off on the side of your page, quickly write down sine theta equals O over H. Substitute in the values for O and H that we're using, do the rearrangement yourself, make sure you know how to get that. If you're confused by this, make sure you know how to get it. All right, so that will just equal, our U was 88.3. Our sine theta is sine of 34.5. And we can chuck that into a calculator. Has anyone beat me to it? Say again? 50.01. That sounds reasonable, absolutely. 50.01, was it? Yep. 01, squeeze that in there. Meters per second. And we can establish that that's going to be upwards. Okay? Positive, right? Upwards. Right, so that's our initial vertical velocity. So now for this formula, we know G, we know Sy. It might not be clear to you what Sy is yet, but we'll talk about that in a second. We know Uy. Now we're trying to find Vy over at this point, okay? This is the Vy we're looking for. How fast we're going downwards at the point of impact, okay? Because we're looking for eventually the time of flight. We want to know from beginning to end. Now, the displacement at that point is this displacement here. It is not this displacement here, because we're going from start to finish. All we care about is that little drop from there to there, whatever that distance is. And that just so happens to be the height of our cliff, which is 60 meters, right? You can imagine that this was being launched off a cliff that looked like this. That's 60 meters high there. It lands on the bottom of the cliff, you know, there, right? Okay. Hopefully that's clear enough. If it's not, draw a diagram. Draw a little diagram, a bit more neat than what I've squeezed in here, because I'm trying to fit everything in here. Off somewhere, draw a diagram of a cliff that's 60 meters high with an initial launch velocity. We've found the y component of that. We're now going to look at that displacement. All right, let's take this formula and go on to the next page. Everyone with me? Anyone need 10 more seconds? Let's do it. I'm going to have to keep flicking back. So we want Vy squared equals, what is it, 2GSy? 2GSy, help me out here, plus Uy squared. Have I got that right, guys? Yep. And our Uy was 50.01. MS, the -1. I didn't say to the -2, did I? Hope not. Our Sy is what? -60, thank you. Definitely not 60, -60. G is just -9.8. Don't forget, -9.8 in this case. And we can solve for Vy. Let's do it. Vy, sub our numbers in and solve. Vy squared equals 2 times -9.8. That's going to be a negative until we multiply by -60. That's going to make it a positive. Plus Uy, which is a positive number, 50.01 squared. Now, check this out. This is where things get a little bit interesting, all right? So like I said, this is going to cancel to become a positive. Plug that into a calculator. Anyone beat me to it? Plus, in brackets, 50.01 squared. That's going to be a big number. 3,677 meters per second. Or, well, we won't worry about units yet because we still have to square root both sides. So let's do that. Vy squared, square root of that. Vy equals. Now, I'll just pause here really quickly. We're obviously going to get a positive final velocity here. Now, that doesn't make sense, does it? Because we're going downwards. But here's why we were correct to use two negatives there, negative displacement, negative gravity. If we had used a positive displacement there, we would have been trying to take the square root of a negative number. Can't do it, all right? So the mathematics here will work out for our mathematics, but we still have to assess our final solution and say, all right, this is a final velocity. This is acting downwards, all right? The math doesn't help us there. That's where the physics is, okay? Your answer to this should be 60.64. And let's establish that that is a final velocity. It is down. This is a V, not a U. It's our final velocity. It is down. which we could now say is negative 60, based off our system that we've established. Okay, is that fine? Cool. Now we just use that. We are now at the point of solving just like we were over here. Okay, we're now back to this. We can now use this exact formula here. Where did I do it? Oh, it was later than that, sorry. It was over here. We can now use this formula here. Vy equals gt plus uy. We're rearranging for t, so Vy minus uy. Subtract uy from both sides. If I take it away from there, that'll cancel on that side, and I'll be taking it away from here. Then I will also divide both sides by g, so that'll get divided by g. It'll cancel on this side, and this side will have a divide by g on the whole thing. And we'll be left with our t, which will equal, and I'll do a little bit of dodgy sort of horizontal transposing over here, 60.64 minus our uy, which was, where did we write it? 50.01 divided by g. Now, g is a negative here, negative 9.8. Our answer, therefore, is going to be negative, okay? That's where we needed to think about the fact that this here is actually... Right, exactly. So at this point, we should stop and go, hang on, something's not right here. What's not right? This has to be negative. Again, this is where the physics comes in. We need to establish this is downwards, therefore, this is negative. Vy is actually negative 60.64. If we don't do that here, then we get the wrong answer. All right? And that makes sense in this math, right? If we took the difference between them and it was only 10, and we divided by how quickly we were accelerating, what we're saying is our velocity changed by 10 meters per second. Our acceleration is 10 meters per second, roughly, squared, right? So we would have only been traveling for 1 second in that case. That's not the case. Our velocity has changed from positive 50 to negative 60. It's changed by 110, okay? It's changed by much more than that. Our velocity has changed a lot. It's gone from 50 upwards to negative 60. So this works out a lot better mathematically. We end up with, anyone beat me to it? 11.29? Yeah? 11.29 seconds. And we, of course, get our negatives and negatives to cancel out. So we realize there, hey, this is going to give us a negative time, something's not right, okay? The numbers should work out, all right? The math should work out. But there are cases where we get a magnitude as a solution and we need to establish its direction. We need to think about that. Bit of problem solving. Cool. Time of flight. That's a lot, yeah? Really, that's two parts. There's two parts to that. The first part is the new part. It's the problem we have to cope with the fact that we don't know the final velocity like we did in the original problem, because the original problem was symmetrical. You can, in example 2, for case 2, use your final velocity of 0, and you can get half the time of flight, except it's not half, because the last part of the time of flight here is more than 0, is more than double that. It's longer. It's not a symmetrical problem anymore. All right? Stop, digest, check your notes, ask questions. 2 minutes. Yep. You want me to look at something? Always. The combination level that All right, no more questions? Let's get back into it. Finish off this problem. All right. Focus up for me. So the next thing that it asks is the impact velocity. Now, depending on how well you're following along, you may or may not realize that that's very easy, okay? We know our initial horizontal velocity. We haven't actually calculated it yet. But we know our initial horizontal velocity because it's just the vector component in the x direction. Instead of sine, which we used for the vertical, it'll be the cos, rearranged cos. So we can very quickly do that now. So let's go, I'm going to go to another page. We're continuing down here. So we're doing part B. We're finding the impact velocity, which is v, okay? And they want it as the vector, not the components. They want the whole thing, okay? We know that v is going to be found from the square root of vy squared and plus vx squared. Okay. I won't use that. We know that from we're basically solving for this. It's going to have some y component, some x component. So it's just Pythag. Okay, we're solving for our hypotenuse, c squared equals a squared plus b squared. Rearrange that, we get that. We know vy, okay? In fact, we probably actually already know vy squared, more specifically. We found it back here, 60.64. Vy equals negative 60.64. Do we know vx? Nope, that's what we need to solve for very quickly. We know that vx is just going to be, like I said, the cos version of the rearrangement here. That's a theta. Don't argue. I don't know why he has a tumor. It's not a tumor. V was 50.01 times by cos of, what was our angle? 34.5. What's up, Brandon? The V, the actual V. Yeah, sorry, you're absolutely right. Sorry, I'm thinking of uy. The actual... Wait, what am I doing? This is u. I'm solving for u. Because ux is equal to vx. Sorry, I messed that up. Hang on, so let's just establish very quickly ux, okay, is equal to vx. Yeah, horizontally we are not accelerating. Our final velocity horizontally is the same. So if we know ux, we know vx. So we're solving here for ux, which is u cos theta, and u was 88.3. Thank you. Sorry, guys. Yeah, I mixed myself up there. Cool. So if ux equals this, then ux equals, our answer there will be 72.77, yep. Therefore, Vx equals 72.77. Now, thinking about how Pythagoras theorem works. Don't laugh at my voice breaking, mate, just because it's on video. Thinking about how Pythagoras theorem works. Are we going to use our negative value here for Vy? Pythagoras theorem a physics sort of concept? No, so it's purely a mathematical thing. There's no point to having a negative direction in our mathematical solving here. So this V is just going to come from square root of 60.64 squared plus 72.77 squared. Now, if you did use a negative vertical velocity here, you would get the wrong answer, okay? Because Pythag doesn't interpret a negative number properly, all right? And in fact, you could produce an unsolvable problem if you use the negative in the wrong way here, because you would end up having to take the square root of a negative number if this was the one that we said was negative, okay? So you need to sort of separate out these mathematical components and these physics components. All right, and that will equal 64 squared plus 72.77 squared. Square root of that, 94.72. That's a 9, 94.72. Last part, very quick and easy. Yeah, Sx equals Ux t. We know all of those pieces of information. We solved for t before. It was 11.3. We know our horizontal speed is 72.77. Sx equals 72.77 times by 11.29. (1,047.37 meters). That makes a lot more sense. What did I do? I did 72 for some reason. I mean, I did 92. I accidentally hit 9 instead of 7. What is it? 821.57 meters. Yeah, that works a bit better. Okay. 2 big examples of this. Case 1 and case 2, one major difference. We don't know the final velocity negatively, downwards, because it's not symmetrical. We also can't use that middle point as a 0 final velocity and just double our time, that's not how we approached the first example. We didn't do that, but that is an option available to you, and sometimes that is useful. So big difference with case 2, we don't know the symmetry, so we can't just find the vertical final velocity really easily by flipping it. Case 3, one other difference. It's the same as case 2 except for one other difference. What is it? It's in your notes. When we outlined the 3 cases, I gave you 3 key differences. Say again? Nice and loud.
Sy is positive.
Sy is positive. Beautiful. Okay, that's the only thing that changes, and that is going to affect where we spoke about where those positives and negatives come into things. That is going to change things here, all right? This will not be a positive. Now, you will have to think about what that means for your actual solution, all right? If you've got a negative value there in this calculation when you're finding that final velocity, you've got a negative value here, you sure as heck better hope that this becomes positive in the end. And of course it should, because this is squared, so this is always going to be quite large. Okay. All right, thank you guys. That third example, I'll have to leave to you as an exercise. It will come up in your chapter review as a question. There's nothing new to it. It's just remembering those niggly little details around when the positives and negatives come into play, when they are useful and when they're not. Okay? Remember, if you're doing Pythag, you don't need those negatives. They mean nothing. If you're using a physics formula, you'll have to think about what's positive, what's negative. It's important. I'm not going to come back to that example. I'm not going to have time. We are going to, next lesson, move on to the next content chapter, so chapter 2, that will be. Thank you, guys. Get yourselves ready for your next period.